So let's go one problem at a time, one by one. So that I selected some problems from the holiday, the textbook. So I have like maybe 7 or 8 problems. I don't think we can walk through all of them, but I'll just continue on next session and next week too. So can you read this problem if you can see it?
3 liquids that will not mix are poured into a cylindrical container. The volumes and densities of the liquids are 0.50 liters, 2.6 grams per centimeters cubed, 0.25 liters, 1.0 grams per centimeters cubed, and 0.4 liters, 0.80 grams per centimeters cubed. What is the force on the bottom of the container due to these liquids? 1 liter is 1,000 centimeters cubed.
Okay, so basically now the 3 different liquid, they're poured on the container, cylindrical container. So because of their the density are different, basically that those 3 different liquid, they sitting on top of each other. So if I do, hold on, let me change the color of my pen so that black is probably better. So if you just draw the picture of this container with 3 different liquid. Hold on. So there, so that cylinder has 3 different liquid with different masses, M1, M2, and M3. So we have to actually estimate weight of individual liquid first, and from that we can just estimate total weight out of those liquids. So the first one, the liquid on top of those 2 liquid, then that is W1 weight is mass times gravitational constant G, which is also expressed with the density of the liquid times volume of that. So that basically M1 is same as density times volume. So this is pretty straightforward. So the low one of the first liquid is what? 0.5 liter is the volume, and 2.6 gram per cubic centimeter is the density. If you plug them into this equation, then that should be 2.6 gram per cubic centimeter times volume is 0.5 liter. But you have to convert the unit from liter to cubic centimeter. So you have to apply the unit conversion, which is 1,000 cubic centimeter per liter. And if you also express acceleration constant number G in centimeter unit, then that should be 980 centimeter per square second. So now we plug them all into this formula. Then the weight of this liquid could be expressed with the centimeter and gram and the second unit. So plug them all, then the liter is gone and only leaves that centimeter and the second. That's actually, so this one is gone because they are on the numerator and denominator. So if you plug in the numbers, that should be 1.27 times 10 to the 6 gram centimeter per second square. So can you maybe convert this answer into Newton's unit? So this is MKS unit. So you have to change it to the SI unit. So the Newton is kilogram meter per second square. Can you convert it into the Newton, the SI unit?
Mhm. I got 12.7 kilograms meters squared.
12.7 kilogram meter second square.
Yeah.
Yeah, that's 12.7 Newton. That's correct. Okay, good. So then now we move on to the next liquid, W2. Same thing, same formula. So that is M2G, which is the load 2 times V2 times G. So that is M2, load 2 is 1 gram per cubic centimeter, and volume is zero point 0.4 liter. You're going to apply the unit conversion, 1000 cubic centimeter per liter and 980 centimeter per second square. So that is 0.25 times 10 to the 6 gram centimeter per second square, which is the 2.5 kilogram meter per second square. That is 2.5 Newton. So can you maybe now solve the case for the third liquid?
Mhm.
Is zero point 0.4 liter of volume, zero point 0.8 gram per cubic centimeter density. And you can also figure out the total force exerted on these three liquids sitting on top of each other. That might be M3G, so 3, volume 3Z.
I got 3.14 newtons.
For third liquid, right?
Yeah.
Then now the total force applied to three different liquid sitting inside this container should be combination of the three mass, three weights out of three liquid. So total force, gravitational force should be W1, W2, and W3. So that is 12.7 Newton plus 2.5 Newton plus 3.1 Newton. So that total force out of three liquid must be 18 Newton. Okay.
Mhm.
Okay. Do you have a question? This is pretty straightforward. I don't think there's a problem. Can you read the number 20?
Mhm. The L-shaped fish tank shown in figure 14-33 is filled with water and is open at the top. If D is 5.0 meters, what is the total force exerted by the water, A on face A and B on face B?
So now this is L-shaped container with rectangular shape. And the one side of the container is open. So when you fill this tank up, up to the top, then each phase will experience different amount of pressure. So the phases of our interest is A and B. So we want to actually find out the pressure applied directly from bottom to up to the base and left to the right to the B. Okay, so that's the problem. We have to find out the pressure applied to the two different bases, orienting the different direction. So number A, the base A. Now the force is obviously pressure times area, right? So that's definition. Again, the pressure is the force applied to this given area divided by the area that force applied to. So now the pressure is the density now times gravitational constant h and a g and depth a of this face A and your area A. Okay, so that's the definition of the pressure in the mathematical expression. So now the low is already given, that is water, the density of water, and the G is just the constant value, and the H is what? Here, H, you look at the H. So the top of this container reference point. So from that, depth into the face A is 2D, right?
Mhm.
So from here to here. So you gotta just apply that the depth inside of this container. So the HA should be 2D and the area A is what? This is D. Oh, let me just delete of it. This is D
D
and
squared.
D. So that D square, right? So that is D square. So that is low of water times G times D times 2D times D squared. So now should be 2 low W Z D square. Okay.
Mhm.
So I'm going to give you just formula and you plug the numbers into this equation and tell me how much you got, right?
Mhm.
For number B, the same reason. But one thing you have to remember, this is the relative the force. So you have to add the pressure, the force out of the atmospheric pressure on top of the surface. So atmospheric force out of the atmospheric pressure is 10 to the 5 Pascal times 5 meter Okay, and square, that is D. So you can just find out how much that the force out of the atmospheric pressure. And the force, total force out of that, the atmospheric pressure and then relative pressure at, and, area A should be FA prime, that's total pressure force from atmospheric pressure force plus relative pressure on the A. So that is from this two, one, and two. Okay, number B, same way. Now, instead of that, the face, the A facing down, that face B facing left, right? So you have to first find out that where that the B actually located. So you apply the same idea. Force B, relative force B is pressure average over the surface B times area B. Here, that is also same expression like A. Low, the water of the density of water times G. Now, that is, hold on, HB times AB, area of the B. So the HB is average depth on that's the face B. So that is here, right? Middle of this face B. So this is 2D, and this is what? Half D, right? 0.5. So from middle of this plane B to the top of this container is how much?
2.5D.
Yeah, 2.5 D, right? So
Mhm.
depth HB should be 2.5 D, and the area is same as A, so that is D squared. So relative force out of this pressure should be low W G 2.5 D times D squared. So that is low W. Oh, gotta just plug 2.5 first. 2.5 low W G D cube. Oh, this should be cube too. I forgot. So that is the relative force out of that face B. Now, just like force A, you have to also estimate the absolute total force on applied to the base B, which is B FB prime. That is the atmospheric force plus relative force from the surface of that base. So that should be combination of this one, three. Oh, that should be two plus three. Okay. So now what you need to do is plug the numbers out of this formula. I mean this problem and into this equation, and then tell me how much you have. Still working on it?
Um, yeah, where is PA on the calculator?
Which one information do you need?
Um, FA prime.
FA prime?
Yeah.
That's what you have to find out from the F naught and FA. FA is right here. And the density of the water is 1 kilogram per, that is actually 1,000 kilogram. Hold on. This actually, I suppose you already know that number, but let me give you a low. W is 10 to 3 kilogram per cubic meter. Okay.
Mhm. But in the equation above FA equals F prime plus FA, it says 10 to the power of 5 PA.
Are
What's
you talking about this one?
yeah.
Yeah, that 10 to the 10th of 5 PA is Pascal, unit of the pressure. And this one is area of top of surface.
Hmm.
Do you understand why do you need to add this atmospheric pressure to the pressure from water itself?
Um, no.
So basically, so let me explain one more time. So the pressure applied to this surface, the FA itself is just force from the pressure provided by this water itself, only water. Water gives some amount of pressure to this surface A and surface B, right? That's
Mhm.
FA and FB. But on top of that, this top of this container also under the pressure from the atmosphere. So you have to add pressure from air, pressure from the water. That is FA prime. Pressure from air, pressure from water on the face B. That is FB prime. Okay.
Mhm.
So top of the container also under pressure. That pressure should be added to the pressure from water itself to the phase A and B. So FA is only from water. FA prime is water plus air, atmospheric pressure. Okay, so FA, F naught is normally given by this number, that's constant value. So they have to, that is the FA, the PA is normally the atmospheric pressure is 10 to 5 Pascal. That's the unit of the pressure. And you have to, in order to find out total force on exerted on the surface of the container, you should be applied the area of the open container. I mean, area of the open container, right?
Mhm.
So area is d squared. Here, d is 5 meter, right? So you have to apply 10 to 5 Pascal times 5 meter squared. That is pressure atmospheric, the force out of the atmospheric pressure. Is this something you're looking for?
Yeah, I just didn't know that Pascal was a unit.
Oh yeah, the Pascal is unit of pressure. If you just Pascal times area is force unit. That is Newton. Got it?
Mhm.
Okay.
For A, I got 4.95 times 10 to the power of 6.
Um, A is total is how much?
4 point,
FA 5,
4.95 times 10 to the power of 6.
Okay, that's good. What about B? B
Um, 5.51 times 10 to the power of 6.
is 10 to 6 Newton, right?
Mhm.
Okay, all right. Let's move on then. Okay, number 24, can you read it?
Mhm. In figure 14-35, water stands at depth D equals 35 meters behind the vertical upstream face of a dam of with 314 meters. Find the net horizontal force on the dam from the gauge pressure of the water and the net torque due to that force about a horizontal line through O parallel to the long width of the dam. This torque tends to rotate the dam around that line, which would cause the dam to fail. Find the moment arm of the torque.
Okay, so the first question is you got to find out the horizontal force y to the dam from the gauge pressure of the water. So if you had if there force exerted on that dam horizontal direction, then you can maybe just set up unit area inside of this water. You can find out the force applied to the given unit surface. So if it is dam, I'm just trying to draw that the some given area. So if you stay inside the water in vertical direction, your position could be expressed with arbitrary variable y. So relative depths of your position from the surface of water on the dam is y. So with that, the variable, you can express the cross-sectional area of this water reservoir to be given by variable denoted inside in this problem. So the width of this, the dam is W, right? And depth of arbitrary position in the water is y. So the given size depth of this cross-sectional area is dy. So with that idea, if you take the unit volume of a given area of interest, could be expressed with the W. So I'm just taking that cross-sectional area like this. So I'm going to simplify this drawing into this rectangular shape, so that the width of this area of water is W, and the horizontal distance could be expressed with the variable x, and the height of this area could be dy. Do you understand why I just take this area out of this water water tank?
Yeah.
To find out the pressure on the given area to the dam. So you can actually set up some simple area to test, drive the formula of the gauge pressure of water at depth y. So number one, the low, the P gauge pressure of the water at depth y is density of the water times G times Y, because that's your position. And the pressure could be also force divided by the area. So here, force is obviously the mass of, the weight of this water inside of this given rectangular area, which is mg. If the mass of the water is m inside this area, so you just replace F with the mass times of a gravitational constant, acceleration constant value G, and the denominator A, B, that's A is the W, X, right? So if you look down of this box, then the area of top or bottom is W times X, right? That's area. So now if you replace M with the density, that should be low times volume times G divided by W X. Volume also could be expressed with W X D Y. Oh, actually Y. And then now if you take that small area then should be expressed replaced with y. But if you think of that total volume of the area of the water from the surface of this dam, then that should be y, and that is times g, and the denominator is w x, right?
Mhm.
So now if you take that wx out of the denominator and the numerator, and that should be low y g. That's why you have that the gauge pressure of the water is with this expression. Now you want to just estimate the force in the given small area of dy in the depths. So the pressure, the force should be P times dA. So now the P is low G Y. And now you want to estimate the horizontal force. In that case, your cross-sectional area is dy times W because force is applied to horizontal direction, right?
Mhm.
So the area should be this side surface. So now dA should be W dy. So now what you have to do is integrate this force from 0 to d because total depth of this water is d, right? So you have to integrate the force df from 0 of the surface down into the d of water, d. So now you plug that the low g y w d y into this formula, then integral of the force would be integral of low g y w dy from 0 to d. Now the low g w is constant value that could be out of this integral, so that low g w integral of y dy from 0 to d. That is total force exerted on this cross-sectional area of this the of interest.
Mhm.
So now that is the 1/2 low g w d squared. That's force, the horizontal force applied to this cross-sectional area in horizontal direction. So now, can you plug the number into this formula and tell me how much you have? This low is, as I only give you, the density of water is 10 to 3 kilogram per cubic meter. And G is, you already know, 9.8. And W is 314 meter. And D is what? 35 meter.
Mhm.
Tell me how much you got.
I got 1.88 times 10 to the power of 9.
1.88 times 10 to how much? 10 to
Power
how much?
10 to the power of 9.
Power 9. Okay, that's correct. And let's move on to number B. Now, question B is the net torque due to the net that force about horizontal line through O parallel to the long width of the dam. This torque tends to rotate dam around the line, which would cause the dam to fail. So let me just get lead on some of this writing from this whiteboard. So So you have to the torque itself is defined by the radius of rotational arm times cross products the force started on the acting point. So now the B you have them the force apply. So hold on is here apply to point O right there. So that's force itself. Let me change the color. So O. So the force actually applied to this direction, F, that F. If this direction is X and the vertical direction is Y, then force itself, Y horizontal direction, as already indicated in the question A. Now, you're standing inside of the water with the depth Y, then the torque applied to this position Y from the force Fx is given by this radiation, effective radius d minus y times force Fx. So here, unit torque applied to this system should be the force Ef applied to point O times radius of d minus y. So here, df is, as I already show you, that the low g y w dy now multiplied by d minus y of the radius, right?
Mhm.
So now all you need is to actually estimate the total torque from zero of the surface of water down to the B. So you have to integrate this torque from zero to D torque, and that is zero to D, the low G, Y, D minus Y, W, dy. Okay, now basically, just like the integration of the force, you just take the same steps. So just take the constant values out of this integration. So that is low G, uh, low G, and the W, and integral of D minus Y times Y dy from 0 to D, right? So from that, if you do the integral of this formula, then that should be low G W times 1 over D cubic minus 1 over 3 D cubic D, okay? So if you finish up this derivation, that should be same as 1 over 6 low G W cubic D. That is torque exerted on this point O by force out of this water, horizontal force from the water onto the point O. Okay, so
Mhm.
now low is what? 1,000 kilogram per cubic meter, and G is 9.8, and W 314, and D is 35 meter. So how much that will be? So let's take a look. You can quickly do the math yourself, right?
Mhm. I got 2.2 times 10 to the power of 10.
Yes. Okay, that's good. Number C then. C, then we got to find the moment arm of the torque. So that the torque itself is R radius times F is R is the moment arm of the torque. So if you move the torque, if you divide torque by force F, then that should be the moment arm of the torque or radius of the torque. So that torque itself is 1/6 G low, low G times W cubic D over 1/2. The force itself is 1/2 low G W D square. If you do that, then low it cancel out of the numerator and denominator, low GW, and D that cancel out, then only leave the D. So that is 1/3 D. So D is 35 meter, so that should be 11.7 meter. Got it?
Mm-hmm.
That's pretty straightforward. Do you have any question?
No.
Okay. We can maybe solve one or two more example problems and then wrap up today's session then.
Okay.
Okay, 32. Can you read this problem?
Mm-hmm. In figure 14-38, a cube of edge length L is 0.6 meters and mass 450 kilograms is suspended by a rope in an open tank of liquid of density 1030 kilograms over kilograms per meters cubed. Find the magnitude of the total downward force on the top of the cube from the liquid and the atmosphere, assuming atmospheric pressure is one
ATM.
atm. The
Yeah.
magnitude of
That's atmospheric pressure.
the magnitude of the total upward force on the bottom of the cube and the tension in the rope. Calculate the magnitude of the buoyant force on the cube using Archimedes' principle. What relation exists among all these quantities?
So that you have some kind of object attached to the wall, the roof, the ceiling of the wall, and then the length of the edge is 0.6 meter, and the mass of that is 450 kilogram, and that has slightly higher density than the water itself. So if you leave that object inside water, obviously it will sink. But there's a string that is suspend the object inside the water. So number one, you're gonna find out the magnitude of the total downward force on top of the cube from the liquid and atmosphere, assuming the atmospheric pressure is 1 atm. So let's take a look. So the surface of this cube is L of 2.5 L below the surface of water. So let me change the color of this. The depth H of top of this cube is L of 2, right? Mm-hmm. And because the pressure on top of this cube should be pressure of atmospheric pressure, because the air itself also provide pressure on the surface of water. So the water itself also is under the pressure. So that pressure should be added to the net pressure of this cube, because whatever the pressure this cube experience is combination of the pressure from water itself and the pressure from the air, as I already explained with the previous example. Mm-hmm. So that is the atmospheric pressure plus the pressure from water, which is low G H top. So you should be familiar with this concept now because we already went through this definition many times. So now the PATM is about 1.01 times 10 to the 5 Pascal, as I only told you before.
Mhm.
And low is now is cube, density of the cube is 1030 kilogram cubic meter, and the G is 9.8 meter per second square, and H top is how much is that? L is 0.6, so the half of that is 0.5, 0.3 meter. You plug that should be 1.04 times 10 to 5 Pascal, or you just probably find out that the equivalent unit of Pascal. So now you estimated the force, I mean the pressure on top of this cube. The next step is to estimate the force out of definition of the pressure. So the force on top of this cube is pressure times area, right? The pressure is now 1.04 times 10 to the 5 times 10 to the 5 Pascal. And the area is how much? L. That's cube, so that's should be like this. So that's L and L, so the L squared, right?
Mhm.
So that is the 0.6 meter squared. So you plug them all, then that should be 3.75 times 10 to the 4 Newton. Okay.
Mhm.
Then number B, now we got to estimate also magnitude of a total upward force. Now we estimate the force, downward force from, I mean, on the surface, top of this cube. Now we want to estimate the force upward to the bottom surface. Okay, that is number B. So the similar way, the bottom of this cube is how much? L plus L over 2. That's the location of this bottom surface
Mhm.
relative to the surface of water. So that is 3L over 2. And you do the same thing. The pressure of bottom of the cube is the atmospheric pressure plus the pressure to the surface of phase from the water. You got to do it. Then that should be how much? That is 1.01 10 to 10 times 10 to 5 ATM, and this is Pascal, plus 1030 kilogram per cubic meter times 9.8 and meter per second square, and the bottom is 3 over 2 times L.6 meter. You plug them all, then that should be 1.1 times 10 to the 5 Pascal. Now, the force is just like question A. Force applied to the bottom face is the pressure of bottom times area A. So that is 1.1 times 10 to the 5 Pascal times area is 0.6 meter square. That should be 3.96 times 10 to the 4 Newton. Okay. Do you have any questions so far?
No.
Okay, so now next step is to estimate. Next question is we gotta so basically this cube is attached to the wall with the rope. And question C, and how much tension possibly apply to this rope to suspend that cube inside the water. So there are few forces you have to add into this estimation. So basically, cube itself has the gravity, that gravitational force pull the cube downward, and there's force from the water. So as you remember, buoyant force is the difference between the two different faces onto the object inside the water. So let me delete some of this writing. So let me quickly just give you a whole picture of force dynamics. Number C. So number C now, obviously tension applied to this rope is upward, right?
Mhm.
And gravitational force downward, G, that is tension Ft, and force from the water upward on the bottom is F bottom, that is upward, and the force from water on top of the cube is downward, that is F top. So that is the net force applied to this system. Tension of the loaf applied the upward, and the gravity is downward, and the two forces opposite direction. So from that, the net force should be based on the Newtonian system. That's Ft. If you think of the upward, the positive direction, then Ft minus mg gravitational force, and that buoyant force normally is the negative pressure, negative force. So you have to just apply the negative sign to that. So that's the F bottom minus F top should be equal to 0. Okay.
Mhm.
I'm sorry, that should be yeah, that should be plus sign. Sorry. So the net force is like this, right? So that is net force existing in the system. So that as long as this cube stay at rest without any movement, that force should be equal 0, because that means like acceleration on the system A equals 0. So that is F equals ma equals 0. So there's no net force. So if you rearrange this in terms of the tension Ft, then that should be mg minus F bottom minus F top. Does it make sense, right?
Yeah.
Okay. From that, well, all you need is to plug in all the numbers. So, how much you have? That mg is, how much is the, wow, that 450 kilogram. The mass of cube is 450 kilogram, and the g is 9.8 meter per second square, minus the force, the bottom. How much is that? That is 3.96 times 10 to the 4 Newton, minus that the force on top of the cube from the water is 3.75 times 10 to the 4 Newton. So can you tell me how much you have from this?
I got 2,310 newtons.
Okay, that's good. 0.23 times 10 to 3 Newton. Okay, I think that's for all today. So we're gonna move on to